All right, so this is an example of what's called the goodness of fit test. This is number 5 on your assignment. A researcher for an automobile manufacturer wishes to see if the ages of automobiles are equally distributed among 3 categories. Categories are less than 3 years old, 3 to 7 years old, and 8 years or older. A sample of 30 adult automobile owners is selected. The results are shown. So if those 30 people are equally distributed among the 3 categories, how many should be in each category? Should be 10, right? 30 divided by 3 should be 10. But when you go out and get a sample of 30 people, even if these are equally distributed out in the population, you're probably not going to get 10, 10, 10 very likely. You've got sampling error. Sometimes you get 8, 10, 12. Maybe sometimes you get 9, 11, 10. Maybe sometimes you get 9, 9, and 12. Okay? So how close do these numbers have to be to 10, 10, 10 to actually agree with the claim that people's cars are equally distributed among these categories? That's what we're trying to figure out. We're going to do it at the alpha equal 0.05 level. That means there's a 5% chance of type 1 error. There's a 5% chance that even if the null is true, that we may reject it anyway. Okay? So at this level, can it be considered that the ages of the automobiles are equally distributed among the 3 categories? What would the results suggest to a tire manufacturer? So that's the problem. Could someone flip the lights on for me, please? Thanks. So you can see I've set a chart up over here, and the observed values are the values you actually get from your survey or from going or calling people or whatever. So they talked to 30 people, 30 adult car owners. 8 of them said that their car is less than 3 years old. 10 of them have cars that are 3 to 7 years old, 12, 8 years or older. That's the observed values. The expected values is what you'd expect. Well, if they're equally distributed, what would we expect in each box again? 10s, yeah. If it's 30, equally distributed, the expected values are 10, 10, and 10. We're doing hypothesis testing. We're doing the traditional method. Start off by writing your null hypothesis. The ages of the automobiles are equally distributed over the 3 categories. That's your claim. The alternative hypothesis would be the ages are not equally distributed over the 3 categories. Second step is to find your critical values. Your critical values are going to come off your chi-squared table, chi-squared chart. I've got that copied on the back of your assignment sheet. Because of the way the formula is set up and that we're squaring things coming out, these are always going to be right-tailed tests. Okay? So when we look for our critical value, which is step B, chi-squared distribution is generally skewed right. We're going to be looking over here on the right side. So on your table, you're going to go over to 0.05 on your chi-squared chart. Your degrees of freedom is the number of categories minus 1. So in this case, there are 3 categories, so degrees of freedom would be 3 minus 1. So if you look up your critical value under alpha equal 0.05 on your chi-squared chart, you get 5.991. If our test value ends up larger than that, then we'll reject the null. If it ends up smaller than 5.991, we won't reject the null. Remember, the chi-squared values start at 0 and they're positive. Any questions so far? Third step, find your test value. Your test value is a chi-squared value, and you find it using this formula. You take your observed value minus your expected value, you square that difference, you divide by your expected value. This means you take the sum of those. It's going to look something like this. Observed minus expected, so 8 minus 10 squared over 10. Plus, because of the summation symbol there, the sigma. 10 minus 10 squared over 10. So again, the O means observed value, the E means expected value.
You have to do it with all 3.
Yep, you have to do it for all of them. Yep. 12 minus 10 squared over 10. Turn this off. So 8 minus 10 would be negative 2. Squared would be 4. So you get 4/10. here you get 0 over 10. So you get 12 minus 10 would be 2 squared, 4/10. So we end up with 4/10 plus 4/10, 8/10, or 0.8. Any questions about how I calculated that?
How'd you know the expected values were always going to be 10?
Okay, because there were 30, if you add this up, 8
Yeah.
plus 10 plus 12, you get a
Just
total.
find the mean.
Well, you just take 30 divided by 3. This says equally distributed, means you have to split those 30 people into 3 equal categories, so 30 divided by 3. Okay? So your test value of 0.8 falls about right there. A little to the right of 0, to the left of that number. So step D would be do not reject the null. Because the test value did not fall in the rejection region. So if I'm not rejecting the null, and the claim is the null, I would say there's not enough evidence to reject the claim that the automobiles are equally distributed over the 3 categories. There is not enough evidence to reject the null that, let's say, instead of the null, let's say the claim. Not enough evidence to reject the claim that the ages of the autos are distributed equally over the 3 categories. In other words, 8, 10, and 12 are close enough to 10, 10, and 10 that we can't reject that they're equally distributed. Okay? These numbers are close enough. In fact, statistically, these values are pretty close. I know that because we got a very low test value. Okay? If we would have got a high test value, a test value bigger than 5.991, that would tell me that statistically these numbers are a long ways apart. Okay? So a high squared value out on there's going to be a lot of times you're going to have a difference. This type of a difference. Because the curve's higher here, right? So it means that's going to happen often. This curve should look more like that out here. This type of thing doesn't happen very often. So if you have a big difference here, then your test value would have been out in the tail out here.